And we're live. Excellent. And that's the wrong screen. Disorientated for everybody. Let's do this one. If I plugged in the HDMI cable. There we go. Excellent. Okay. Okay. This is the last element of our useful code that we need. There, we're bright. Excellent. What do I mean by useful code? Well, as I've mentioned, and I have mentioned over the last couple of weeks, we have 5 elements that we want to ensure that we have comfort with. I won't say mastery yet, but I'll say comfort with, to make sure that we can do interesting problems, that we can solve interesting problems. What you're going to notice is that from this week onward, the problems are going to get more complicated, but we don't necessarily learn any new structures inside programming. We are going to reuse these 5 elements over and over and over again in different combinations to be able to solve our problem. So our first one was output to the user. We were able to do that. And that can be true just printing out text in quotation marks or solving equations. The next thing we looked at was the idea of variables. We can store information. So we can do a calculation and we don't need to keep redoing that calculation. We can store it in a variable and it's then held, we're saving it with processor cycles, which leads us on to user input. So we can take a value in from the user, we can store it in a variable, and then we can use that value which the user entered in inside our programs. And that means that we're able to add a little bit of dynamic elements to our program. We don't know what the numbers the user is going to enter in. So we have to make sure that our program is robust enough that it will work for all numbers. And then we looked at the idea of taking questions. We can ask questions of our program. And depending on the value inside or the value of the variables, the question may be answered in different ways. Has the user entered a number that is positive? Or have they entered a number that's negative? Have they entered in an even number? Have they entered in an odd number? Have they entered in a legitimate date? So that the day number, the month number, and the year number all match up to something you can find in a calendar. The last thing we're looking at is the idea of loops. And loops are the ability of doing a section of code more than once. So think about the code that we've written so far. Up until last week, our code started on line number 1 and ran down to whatever the last line of our program was. And then last week, we introduced the idea of if statements, which meant that we could still start at the top of the code and work our way down, but we had the opportunity to skip sections or to go into sections depending on the values in our programs. What the loop is going to allow us to do is to incorporate that we repeat certain sections. So think about the guessing game question you have, the last question you have in that workbook. If you take a number in from the user, if they don't get it right, if they don't guess the right number, you have to take in another number. You have to keep doing that. So the code to take a number in from the user, check if it matches the number they're trying to guess, tell them whether it's too high or too low, that section of code would be repeated 20 times, or has the opportunity of being repeated 20 times, or maybe only 10 times, or maybe only 3 times, depending on how good or how lucky that user is. And that allows for even more variance in how our code works and how the code is structured. And building on top of that, we're able to combine our questions, our if statements, and our loops together in different formats to do different things. One of the questions we're going to do tonight, well, if we go through the full 3 hours, will be we will look at how to tell the user whether a number they've entered in is a prime number or not. And we'll do this through loops and if statements. And once we know how to work out, how to evaluate what a prime number is, it's just a matter of writing the code for that. And if we have enough time, we will get the user to enter in a number, let's say 100, and we will tell them all of the prime numbers between 1 and whatever number they enter in. So how do we write loops? Well, we're going to look at a couple of loops this year. At minimum 2 with the possibility of 3 loops. And the first loop we're going to look at is a while loop. Now, each of the subsequent loops we'll look at have the same basic structure, but some of them are better suited to some types of problems and some of them are better suited to others. The while loop is an all-rounder. It can solve any of the iteration problems we might have, any of the problems we need to repeat a section of code. It doesn't matter what the condition is. And if you look at this slide here, and if you remember the slide from last week when we looked at if statements, the only difference between that slide and this slide is the word while. Last week I had if. But apart from that, it's exactly the same structure. We use the keyword while, which is going to indicate to the program this is the start of a loop. We have our brackets, and inside our brackets we have our true-false expression, or our Boolean evaluation. And very much like our if statements last week, we need to be writing statements that can only be evaluated to true or to false. Because that is the guard, the bouncer effectively to our loop. It decides whether we're allowed inside the body of the loop to run that statement or whether we're not allowed and we skip down to where the end of that is. I said it last week, and I'm going to repeat myself because it is a really important element of programming. The ability to build Boolean expressions, to construct sometimes complicated evaluations, which will simplify down to either a true or a false answer, depending on the values of the variables, is a really important skill. It's something you need to be able to work on. It's something that's going to be pretty much for every program you're going to do after today, you will end up writing some sort of a Boolean expression, something that's going to simplify to true or to false. And to highlight that, for every exam I've ever written for first year programming, part 1 of question 1 is 10 marks going for 5 Boolean expressions. So that's 10% of the paper, very first part, first question, and you need to write 5 lines of code to get those full 10 marks. And the remaining 90 marks are other stuff. And as I said last week, I tell students this at this time every year. So 1/4 of the way through, they have another 3/4 to work on it. And for the remaining 3/4 of their year, the students write hundreds and hundreds of Boolean expressions of varying levels of difficulty. Some of them are really simple. Is the user input equal to the number we're trying to guess? Some of them are much more difficult. Is the day date between 1 and 28, and is the month date equal to 2, and is the year date modulus 4 equal to 0? Okay, where we can build up a more complicated one. Or is the number the user entered in a positive integer that is not 37? Okay, so in all of those examples, I don't want an actual answer. I want the statement that I could send in values to each of the variables and it would work out, yes, that is true, or no, it isn't true. So the positive, the last one I gave you there, a positive integer that is not 37. What I'm looking for there is that, let's say the variable is x. X is greater than 0, and x is not equal to 37. That's it. But every year, when I ask a question like that, in part 1 of question 1 of the exam paper, I get someone writing down 15. And your sniggers are correct. That's completely the wrong thing. And you haven't had a lot of practice with Boolean expressions. These students have had 18 weeks of continuous repetition of having to use them in their programs. They have submitted assignments to me which usually when you're given a take-home assignment from me, not for your worksheets, but for the actual ones that are called assignments, they are far more complicated than anything I'm asking in the exam, because you've got time to go home to look up stuff, and you've weeks to work on it, not 3 hours to work on it. So I'm amazed then that students can get it right in an assignment, and when I ask a simpler question in an exam, completely right, not even wrong, just do not understand the question. Which highlights two problems. The first problem is always the question of ownership then of the assignments. Was that work actually there? Did someone do it for them? Were they helped? The second thing comes back to what I've been saying probably from week 3. If you don't understand what's been asked of you, and that's going from now up until whenever you finish your degree, ask. If you don't understand the question that's been asked, not how to do it, that's the challenge. That's what you're meant to do as students. But if you don't understand the question that's been asked, the actual English words and what they want, what's expected of you, get that clarified. Get it clarified in the assignment, get it clarified in the class, get it clarified in the exam hall. There is nothing wrong in an exam where there are, whatever, 200 other people putting your hand up and going, I don't understand this question. What are you asking me to do? And the lecturer will be able to answer, well, what I want you to do is write an expression where if I put a value in for the variable x, it will work out if this is true or false. That's not giving you an advantage over any of the students, so I'm allowed to answer that type of question. If you show me a piece of code and said, is this right? I can't answer that. I can absolutely tell you, I can clarify what's been asked. I can clarify what the words mean and what I'm expecting from you. Because if you don't know what's expected of you, how are you meant to answer it? How are you meant to solve that problem? Same thing for every other programming class, every other assignment you're going to get. You don't understand it. Not how to do it, but what is expected of you. Get it clarified. Because otherwise, you're guessing. Okay, so here is our basic structure. We have our while loop. We're going to have our true-false expression, and then we're going to have our curly brackets, which will have one or more statements inside, which are only allowed to run if this expression comes back as true. So it looks like this. Is the true-false expression true? If it is, great. We get to execute the loop of the loop body. Then we go back up, and we check, is it still true? And if it's not true, well then we move on to whatever the next statement is past the end of the loop. This circular action here, this implies that something is going to happen inside the loop body that may change the validity of the statement, that may change it from a true statement to a false statement. Now that could be a couple of things. I'm assuming all of you have read through all of the questions in the workbook. You just literally read the questions. I'm not expecting to have attempted everything yet. If you go back to the last one, where you're talking the guessing game, it says, create a game that will keep asking the user for a guess as long as they haven't guessed correctly. So in other words, the game's over because they've won. They haven't exceeded 20 attempts. The game's over because they've lost. Or they haven't entered a negative number. The game is over because they've quit. So something's going to happen inside the body of that loop that either they're going to guess correctly, or they're going to guess incorrectly, and now they've hit their maximum amount of tries, so they're going to get kicked out the next time around. Or they've entered in a negative number. They've said, "Oh, I've had enough of this," and they've quit. So that's what your loop body is going to do. Your loop body is going to change the values in your program, or have the possibility of changing the values in your program. And that's what's going to move you toward the exit condition. We will assume, for most problems, when you come across the loop the first time, so when you get to the piece of code that says, while, whatever, that probably for the very first time, it could be true. And you'll get into the loop for the first time. And then something's going to happen inside that loop, and it might change some of the values, and you come around, and you reevaluate it. And is it still true? The values are probably slightly different. So you're going to have a look at and see, are they still true? And if it's still true, great. Go in and execute it again, and maybe they'll change again. And you go back, still true, change again, still true. And eventually something will happen where they've changed so much that this statement is not true anymore. And once it's not true, well, then you exit out of the loop body. Does that make sense? Let me give you an example. We are 24th of October. That means that in Wednesday's Halloween. On Thursday of next week. So do you use a machines? You log into machines for chemist class? Yeah? No? No. Okay, so it's not in the lab. Do you have a lab on Thursday with any of the classes? No. Okay, right. If you happen to try to log on to the machines on Thursday, 1st of November, you'll be asked to change your password. Okay? Usually monthly, you're asked to change your password just to make sure that you don't have a password that's insecure and someone can get into your account and start messing with your print credit or whatever it may be. When you try to enter your password, there are certain criteria that they want to check. Let's go with the really simple one. You're asked to enter a new password and verify or confirm the new password. So those two fields have to match. And if they don't match, you're asked to do it again. And if they don't match, they're asked to do it again. So do the true or has the password been set? Or sorry, is the password accepted? No, it isn't. Okay, right. We're allowed in here. So please enter your passwords. Enter first field, enter second field. Come back up. Are the two passwords different? Yes. Okay, back in. Please enter the password again. Are the two passwords? And until you match them the same. And when it comes back to are the two passwords different, and it comes back as no, well then you're allowed out. You log into the machine, it saves your new password, you move on. Okay, so that is an example of a loop inside a computer. That's another example. You're doing computer hardware. How far has Paddy got in computer hardware? Have you got up to the fetch execute cycle?
Boolean.
Boolean, okay. Oh, that lovely stuff. Right, okay. So it would be mean of me to give you a decimal to Boolean converter as your first assignment, yes?
Yeah.
I'm not going to, that's fine. Okay, so as part of, when you get past Boolean, so Boolean is the math that computers run on, and then you start looking at the von Neumann machine, which is the kind of the prototype or the abstract idea of what a computer is. It's got a processor, it's got working memory, it's got storage and other stuff. And then you start looking at how the processor works. And the processor runs on something called a fetch execute cycle, which is a loop. And it goes off, it gets the next instruction, it gets the bits it needs to run that instruction, it runs that instruction, it goes back, it gets the next instruction, it gets the bits it needs to run, it executes it, it goes back. And so it loops around and around and around and around. And it'll keep doing that until you give it a reason to finish that loop. Now, inside a computer, the reason to finish that loop is you go, Windows button, shut down. That fetch execute cycle running in an operating system will run always. If the computer's on and the operating system's running, that's running continuously in the background, trying to finish off any jobs you might have given the operating system. And when you go to shut it down, it closes down that. So basically the loop will run for as long as the machine's on, and then when you choose, hey, let's shut down the machine, the loop finishes, it cleans up all the rest of the bits it needs to do, and it quits the program. In all the examples of the loops that we do, there is the same pattern of actions with slight differences. And that's kind of the key figure with loops. It's basically the same thing, but there are slight differences as you move along through the loop. So let's have a look. Here is a really simple loop. We have our class up here, our public static void main. We declare one variable here, one integer variable called count, and we give it a value of 1. Our loop condition is while count is less than or equal to 3. So what happens the very first time we run it is it goes while count is less than or equal to 3. Oh, count, that's a variable. Get the value for that. While 1 is less than or equal to 3. We all agree 1's less than or equal to 3? Brilliant. We're allowed in here. We run line 8, it prints out the word star. We run line 9, it prints out the word moon. And then it increments our variable. That plus plus means it's going to increase the value of our variable by 1. Come back up. Count now is a value of 2. 2 is still less than or equal to 3, so we're allowed in again. Prints star, prints moon. It increments the value of count by 1. Back up here, 3 is less than or equal to 3. It'll print star, it'll print moon, it'll increment the value here up to 4. 4 is not less than or equal to 3. So it does not let you in here, and it spits you out at line number 12. So it'll print out good night, and then the program finishes. Okay, so that's a really simple example of a loop. What I'm going to do is I'm going to hop out of this, I'm going to copy this code, and I'm going to put it into Jelly to animate what's happening. That there. So when I put this into Jelly and we're running through this example, you will see what's happening, what the evaluation is happening. Okay. Actually, I only need this here. Okay, change the font to. Don't need that one. Okay. So here's my code here. And actually just change the font as well to gold. That makes it a little more readable there. Okay, let's compile this. And we'll play. And I will pause it here. Okay. So what's happening now is we're on line number 5, counts equal to 1, so it's creating its variable up here. So now I'm going to put the value inside that variable. Okay, so it puts 1 inside there, and now it moves on to my next evaluation. So it's going to check, is the value of count, which is 1, is that less than 3? We're going to evaluate that, which is going to come back as true, which allows us into the loop. And so now we start running the lines of code inside the loop. Maybe I should just let it play. There. And then it'll print out moon, and then it increments count. So count has gone up from 1 to 2. We check now if 2 is still less than or equal to 3, which it is. Which means we're allowed into the body of the loop. It prints out star, it'll print out moon, and it increments our count by 1. And then we check to see if that's less than or equal to 3, which it is. So we're allowed into the loop one more time. Prints out star, prints out moon. Okay, so the last thing here, we're going to increment this value here. The reason why I've stopped this is that this is how the loop is going to stop. It's going to change that to 4. We now go back up to line number 6 to reevaluate it. So every time we've been into the loop, we run line number 6. Is this still true? Then we run line number 8, line number 9, line number 10, back up to line number 6. Is it still true? And we keep doing that until we get this where it's going to be false. So now we're going to check to see if 4 is less than or equal to 3. It's not. So it's come back as false, which means that it will not let us into this section here. It'll drop us down to, so it says exiting the while loop, and then it'll drop us down to line number 12, and it prints out good night. Okay, so that illustrates what happens in a loop as we're going through it. Let's change that slightly and do another quick example. So if we're going to edit this, let's say, well, count is less than or equal to 10. I'm going to get rid of all the printing statements because they're kind of irrelevant inside Jelliet. It also means that I can, well, make this code slightly bigger. That's probably too big. Okay, that's as large as I can make it. So again, what happens is we create our counter, we give it a starting value of 1, and as it goes into the loop, it just checks, is the current value of our variable less than or equal to the right hand side there, less than or equal to 10. If it is, then all we do in this example here is we increase the value. So it goes to 2. And then we check to see if that's still less than or 10, which it is. And so what's going to happen is that I've deleted the printout lines, but it'll do whatever it needs, and then it'll run line number 8. And line number 8 is the thing that's changing my conditions, that's moving me toward my end point in my loop. In this structure we have here, we have line number 5, line number 6, and line number 8. They're the 3 pieces of code we need to make our loop run and to run properly. Line number 5, where we set the starting value of our counter, is called our initialization statement. It sets up the loop. It allows you the possibility of access. Line number 6 is our guard. It's our limiting statement. It's going to define how many times you can actually use this loop. How many times can you run through this loop? And line number 8 is called our progression statement. It's what moves us from the start point slowly along towards the end point. So that's going to run around. And again, like with the previous example, when I get to a value of 10, it's going to go in and run line number 8 and increase it to a value of 11, and that's where it's going to invalidate this. That 11 is not less than or equal to 10, so it's not allowed into the loop to increase it any further. And this is where we increase it to 11, and then this is what's going to quit out of our loop. Okay, that's the end of our program. Did that make sense, folks? Does anybody have any questions on either this code or on the other example?
It's maybe a stupid question, but
No.
In order for the count plus to work,
Yep.
we have to use the count.
We will. It's
a must.
this variable, so you don't need to call it count. It just needs to be a variable. In this example here, this is essentially a linear progression loop. It moves in fixed increments toward the end. We need a variable to do that, so we need something that's going to change over time. We need our ending point, which is going to be on the right hand side here, and we need some way of changing our variable. Now, this is our first examples of loops. Throughout what I'm going to cover 4 loops between this week and next week, we'll look at examples where we start with a low number and we count up to a higher number. We're going to start with a high number and we're going to count down to a low number. But then we'll look at examples where the loop will go round until the user enters in a negative number. So in that case, we don't know how many times that loop's going to run. We wouldn't have necessarily a count plus here. But that's later on. We'll deal with the more basic stuff first, and then we'll move on to that. But yes, you need something like line number 10 to move to allow the possibility of the loop stopping. If you don't have line number 10, and I can guarantee, without seeing you ever attempt loops before, because every student does this, all of you at some point this year will forget to put in the equivalent of line number 10, and you will get what's called an infinite loop, where your code just runs and runs and runs and runs. So it just prints out pages and pages of star and moon, or whatever the example might be. And the first couple of times you get it, you go, oh God, what's that? And then it's quicker and quicker to go, oh yeah, I left out the plus statement or the minus statement, depending on which is appropriate for your program. But yes, to answer your question, in every program you write, there needs to be some way inside the loop body that a value changes that allows for the possibility of exiting the loop. If you don't have that, the loop will never finish, which means any of the code you've written below, you have no chance of getting it. You will get stuck at that point to go round and round and round. that make sense?
Thank you.
Any other questions before I move on?
Yeah, if you wanted to go to twos, would you change it in both places or would you change it just in one area?
Really good question. Right. So you want to, rather than counting 1, 2, 3, you want to
Yeah.
count 1, 3, 5, 7, up on that. Okay, so excellent question. In loops, the most common way of traversing a loop, so going from the start to the end, is 1 by 1. And because of that, and this is common across programming as a field, but also in all programming languages, the plus plus notation for going up in numbers, or the minus minus notation for going down in numbers, is a shorthand instead of writing, in this example here, it would be count is equal to count plus 1. Okay? If you want to change the increment, the amount that we're going to move each time, you need to write it out longhand. So for example here, if you wanted to go up by 2, it will be count is on line number 10, it will become count is equal to count plus 2 or 3 or 5 or whatever it might be. Okay? So I have about 5 example questions I'm going to do with you over the time it takes to cover loops. And the first question I'm going to get you to work on will be pretty much that. You're going to write a program that's going to take in 3 inputs: a start point, an end point, and the size of the increment. And so it means we don't have to start at 1, or we don't have to start at 10 and count up or down. We can start wherever we want. We can count up or down from there, and we can count in whatever increment we want. But we'll get to that in a little while. Any other questions before I move on? Everyone happy enough? Okay. So here, yes, so exactly. The count plus plus is our shorthand for incrementing true statements. It's the most common one you'll end up using. I'm trying to think. The guessing game question won't be as simple as this. It's a more complicated statement than that. But for a large part of what we're going to do after now, you're going to have a plus plus statement or a minus minus statement somewhere in your code. Because the normal progression of a loop is 1, 2, 3, 4, 5, 6, 7. You just work your way through it. Whether it's counting from 1 to whatever number, whether it's dealing with text processing, where you start at the first character, then move to the second, then the third, then the fourth, and the fifth, whether it's dealing with a collection of data or a text file, the systematic processing of it, where you start at one end and you logically move through every element, checking it for something, is what we're going to spend a lot of the remainder of this course doing. And that will build up your routines and your habits in how to approach problems and how to break them down to smaller components. And like I said, if you want, you can do minus minus, which will decrease. Okay, so this phrase here, this is written on the back of most shampoo bottles. Lather, rinse, repeat. And for us, as intelligent humans, we can read the instructions and go, oh, okay. And you understand that for me to wash my hair, I will follow these steps as many times as is needed. And I'll be the judge of when it is or it isn't time to stop. So if it's a normal Wednesday, you're washing your hair's not too dirty, maybe you just do it once. You've just finished an obstacle race or a mud run or Tough Mudder or something like that, and you're caked in whatever it might be. Maybe you're going to do this a couple of times to get out all of the mud and whatever might be in your hair. We're intelligent creatures. We have common sense. We have the ability to kind of go, I spent 10 minutes washing my hair. I spent 15 minutes washing my hair. I spent an hour washing my hair. I'm running out of shampoo. I'm going to stop now. The water's cold. A computer doesn't have this common sense. Remember, I keep saying that computers are stupid. And because of that, we need to have very clear boundaries of when a loop will and will not finish. We need to have our start point. We need to have our end point or our limit. And we need to have something that moves us toward our end point. If we don't have all of those 3 elements, our loop won't work the way we want it to. If we don't have a starting point, we'll never get into the loop. So however many lines of code we have in there, they're effectively useless. We never get in. If we don't have a progression statement, a way of moving toward the endpoint, we have an infinite loop. It'll just go round and round and round. And if we don't have an endpoint, it kind of is the same scenario. Our loop might end early. It might end right on time. It might end way too far. It might never end. We don't know. It becomes unpredictable. So we need to have those three elements. And I've done this example here. So this example here is almost the same as the last example I did. This is how you sum up the values from 1 to 10. So in this example on line number 5, I declare my counting variable. That's my check to see where I am in the loop. And I declare my summation value, so where I'm going to hold the answer. My loop will go while count is less than or equal to 10. My body of my loop is that the value of sum is the existing value of sum plus the existing value of count. So it starts off with 0 plus 1. So we put 1 in there. We increment count and we go back up. 2 is less than 10. So now we have 1 plus 2 gives us 3. We increase this to 3. 3 is less than 10. We have 3 plus 3 gives us 6. This goes up to 4. And that pattern repeats over and over again. Every time we go into the loop, we do the same actions. We take the current value of sum, we take the current value of count, we add them together, and we put that in as a new value of sum, and we change the value of count by increasing it by 1. And we go round and round and round. This is the key thing that's changing on line number 10, because eventually we will get to the point where count is no longer less than or equal to 10. For us, it'll be when count hits 11. When count hits 11, that's it, we're finished. The loop will finish, it'll come back here to line number 12, where it'll print out the sum is equal to, and whatever the answer is there, which is 55, I think. Okay, so it's the systematic processing of the loop. Is this still true? Go in and run this action. Go in and run this action. Come back up again. Is this still true? And you go down to line 9, line 10, back up to 7, line 9, line 10, back up to 7. Until such time as line 7 is no longer true. At that point, we jump down to line number 12. Okay, so I've already mentioned this. We need 3 things to finish or to make our loop work. We need an initialization statement, we need a progression statement, and we need some way of exiting our loop. We need to initialize before the loop starts. In a while loop, we need to initialize before the loop starts. If you have done programming previously, and you've done something like a for loop, it's slightly different because it's all done in one line, and we'll get to that in a couple of weeks. But for the moment, we initialize before the loop, and we're going to use whatever the result is after the loop. So when the loop exits, we're going to get down here and say, all right, well then that's finished what we want to do. So the way we're going to use our loop is we'll have an initialization, set up all the values to be whatever they need to be. We're going to have our loop body, which is the action that we're going to repeat multiple times. At the very end, we're going to use the result computed by the loop to do whatever we need to do. Okay. What I'm going to do is I'm going to keep going through the slides, and then because there's about 14 more slides left to go. It's not a huge amount of slides in this. But when I finish that, I'll go and I'll start doing iteratively growing examples where we'll start really basic, like what we've done, and we'll make it more and more complex as I go along, and that'll give you a chance to stop me and ask questions as I'm actually running the code. So here is a slightly more complicated problem. I want to display the squares, all of the squares that are less than 5,000. Okay, so what we're looking for is the square of a number, so that number multiplied by itself. And what we're doing our evaluation on is the result. So you can see here, square of 1 is 1, square of 2 is 4, square of 3 is 9. All the way down to the square of 70 is going to be 4,900. But the square of 71 is 5,041, which is above 5,000. So that's what we want to avoid. To do this, we need a way of controlling when our loop exits. This is an example of where we don't have a simple, is this number less than this number? It's slightly more complicated than that. But we also need to remember a shampoo condition. We have to have our exit point. So let's see how we do this. We are going to start x at 1. That's our counter for this example here. Our loop is going to do an evaluation as its guard. And this is absolutely appropriate. You're allowed to do this. Remember, the computers are fantastic at solving mathematical problems. If you can give them a clearly defined problem with clearly defined values, they can solve it incredibly fast. So what we have here is we have x multiplied by x less than 5,000. Because of our substitution rule, when we get to this line of code, we're going to replace x with the current value, which is 1, and x with the current value, which is 1, which becomes 1 multiplied by 1. We can simplify that. So 1 by 1 is 1. So now we have it 1 less than 5,000. And if it is, we're allowed in here. We're to print out the values that we have, and we increment x up by 1. So the initialization in this example is the same as previous examples. I've used a different variable name, but it's basically the same idea. The progression statement is the same. It's just plus plus. We're going up by 1. We check the square of 1, then the square of 2, then the square of 3, then the square of 4. But the bit that's changed, the bit that's got slightly more complicated is this, where we have a calculation that we have to evaluate first, and then we have a comparison of numbers. Remember that when you have this, the bit inside the brackets at the while loop still has to simplify down to either true or false. Monday, with the full-timers, I had some of the students attempting this. They kind of read ahead and they were trying to attempt to do some of the questions. And they had checked that what they wanted to do is they wanted to work out if you can find the square that is exactly a particular number. So if x multiplied by x is exactly equal to 5,000. They're trying to find out that. And obviously they didn't pick 5,000, they picked a different number. But the problem was they didn't, inside here, they didn't use an expression that is a Boolean expression. They had a single equal sign, which meant that it was assignment. And it was actually even a broken assignment value. You had a calculation on one side, and a value on the other side. And when you solve the calculation, well, for you guys, when you solve the calculation on the left-hand side, what it says is take the value on the right and put it into the left. And that wouldn't have made sense either. But the problem was that this statement here wasn't simplifying to a true-false statement. So I said, well, that's wrong. That's not how you write equality. Equality needs two equal signs. And so they went off and they fixed that. I had another student who was doing it, but they just wrote x multiplied by x. And that just gave them a number, which isn't true or false. You can't simplify a number, even the result of a calculation of numbers, you can't simplify that to either true or to false. If you remember from last week, we have our 6 comparison operators. We have greater than, we have less than, we have greater than equal to, less than or equal to, or not equal to. We need, in a Boolean expression, we need at least one of those. If we don't have one of those, there is no way to say the result of this is true or the result of this is false. If we just have an expression that has pluses, minuses, multiplication, division, modulus, that's going to give us an answer, absolutely. But more than likely, it'll give us a numerical answer. To make it a Boolean answer, we need to have a comparison in there. Greater than, equal to, whatever it may be. But there needs to be, and is this less than, or is this the same as, or is this greater than, or is this not equal to something on the other side? Okay, so what happens inside this loop is that we have sorry, that's for the next example. Let's go back here. What we have inside this loop is that we're doing our calculation here. So the evaluation is always done at this line of code. So So we'll print it out, we'll increase the value, we come up here, we do another evaluation, and the processing is all done here. That works for some examples, but it doesn't work for every single example. And sometimes we want to stop a loop before it has to go all the way down through the body and then back up to this point here. And that's called an interior exit. So rather than it being, because the guard is kind of on the outside. So rather than having to go all the way through the loop body and then come back around to the front of the loop again, to the exterior of it and see if you're allowed back in, we want to have the ability to exit that loop from the inside. So what we're going to do is we're going to compute x multiplied by x, and we're going to save it into a variable called square. So this is an augmentation of the previous example. We're going to have an if statement to check if the square is greater than or equal to 5,000. We're going to quit the loop. We're going to get out of the loop as fast as we can. Otherwise, if it's not, well, then we're going to display the square. We're going to increment x. We're going to go back up. We're going to compute x multiplied by x, save it into variable square, and then we're going to run this if statement again. So the loop, from an outside point of view, the results are the same. It will print out the exact same output as the previous example. However, the internal functionality is different. This highlights two things. The first thing it highlights is actually the more important thing. Practically every single problem I will give you, and every single problem you will come across in your programming career has multiple ways of solving it. And when I give an example on the board, that's a sample solution. It is not the only way that it can be solved. The reason why this is important is not to lower your confidence in your own skills. What usually happens when you submit the workbook, or when you submit the assignment, or when I give you a class test and you've done the class test, you go, what was the answer to that? Is that I'll do a sample solution. That's a sample solution, and I usually make quite careful to say, look, this is one way of solving the problem. And so I'll go through my version of it. And your code might be different. Everybody's code will vary slightly because everybody's approach to the problem is going to vary slightly. And the more complicated we make the problems, the more likelihood is that that's going to change. That your code will be different to your code because you think different. You'll have the same approach to the problem because you're in the same class. But when you're off on your own trying to solve your assignment, the way you actually tackle the problem will be different. For first year, I only care about, can you get the problem solved? Can you get the problem solved using the tools that I've given you? So if statements, loops, variables, input, output. If you can do that, it doesn't really matter what way you did it. If you do it this way or if you do it the previous way. Eventually, we will get to a level of programming where we're dealing with what are called classical data structures, an agreed way of solving specific problems. So there are things in programming called queues and stacks and heaps and linked lists, and they have been such a fundamental element of programming and programming structures for such a length of time that everybody implements it the same way, because it's agreed that this is the most efficient way of doing it. But for first year, when you're just kind of figuring out a simple problem like this, I don't really care how you do it. I want to see that you have done it, that you've gone through the work for it. Now, that being said, and it's not really an issue with part-timers, it's more of an issue with full-timers, and I think, again, that's kind of age difference and maturity levels. Don't spend a 2-week assignment looking for a shortcut to solve it. Do the work. Go in, use the 5 elements in whatever combination makes sense to you to get the job working. Every year I'll ask specific questions, expecting you to do them in certain ways. And every year a student inevitably will go off and find some advanced command that does it in 1 line of code rather than 5 lines of code. But the problem was, it does solve the problem. It does solve whatever the question I'd asked. Problem was, I was trying to assess, do you know how to write an if statement? Or do you know how to do a loop? Or do you know how to do a loop inside a loop? And if you go off and get the extra command or put it in, I can't verify if you've learned that part of programming. So I'm usually very explicit in what I'm expecting from you for an assignment. For the bigger take-home assignments, I will give you a matrix of exactly what marks are going for what section, to allow you to say, oh, this is an assignment about loops, this is an assignment about if statements, this is an assignment about whatever it may be. We don't cover a huge amount of content in first year, and the reason why we don't is because I want you to use the 5 elements plus some extra features we'll look at after this week, and to think your way out of problems, to have good problem-solving skills with not necessarily a huge amount of commands. Because what happens then is, as you go further into your career, you go to second year, third year, fourth year, you go out and get employment, you are going to be much more competent at solving problems in any programming language. Because the stuff that we've covered so far is common to every single programming language. But if you go off and find, oh, I found a way to, I talked about prime numbers, a single way, or a single line command to find prime numbers. Well, that might be only relevant in Java or in Python or in C#, and there mightn't be an equivalent in the language you're using today. But if you know how to build it from really basic elements that's common to everything, it mightn't be the most efficient way of doing it. It might take a little bit longer, but you can probably write that code in any programming language. And that's what I want to achieve, because we're doing Java now. There's not a guarantee you'll be doing Java when you go out into your career, when you go out in employment. There's not a guarantee you'll be doing Java next year. Something could dramatically happen that we shift from Java to, let's say, C# or to Python or to some other language. Then that's probably unlikely, because we try to keep a consistent structure as possible. But as you go from first year to second year to third year to fourth year, you're going to see that we're going to incorporate other languages. You're doing HTML and CSS with Gem at the moment. Next year, your web development, you'll be doing PHP. In third year, you'll be doing Python. In fourth year, you do Ruby. You do Android development, which is Java and XML. So we move with the languages as they're going across. You need to be adaptable in different languages. You need to be able to say, well, I don't know C#, but I know how to write a loop. I know how to write an if statement. I know what I want to do. I just need to look up the specific command to get that working in C# or in Python, whatever it may be. So let's have a look at a solution for this. Our interior exit. We're going to compute and save the result of x by x into a variable called square. We're then going to have an if statement to decide if we exit. If we don't run this, if we're not allowed into this if statement, but then we're going to display the value of square, and we're going to increment x. Okay. So there are two unusual lines of code in this example. Everything else should be familiar and comfortable with you. You've seen it all before. The first unusual line is this, while true. If you remember, when I talked about the Boolean guard, the limiter to whether you're allowed into the statement or not, that needs to simplify to true or to false. So if I've set this as true, what do you think that's going to mean? It's infinite. You're always allowed into the loop. There's never a condition where you won't be allowed into the loop. In the same sense, if we set it to false, you're never allowed into the loop. Okay, because true and false are literal values. They cannot change. There's no variance in that. There's no evaluation. It's the simplest form of a Boolean expression, either true or false. So if we set this as true, it guarantees that we're allowed into the loop every time. And because of that, there's no, if we ignore line 11, there's no way of getting out of that loop. That loop will just run and run and run and run and run. But by including line 11, it allows us to exit the loop from inside the loop. That's what I mean by an interior exit. The break command will quit the current loop that you're in. So what happens here is everyone's allowed into the loop. We have 1 here, square is equal to x by x, so we get 1 That 1 is not greater than or equal to 5,000, so we don't get to run line 11. We go down here, we print out the value of that, we increase x, we go back up. True, everyone's allowed in, great. Square is equal to 2 multiplied by 2, which is 4. 4 is not greater than 5,000. We're not allowed to run line 11. We run, hang on.
Mhm.
One minute. Right. Try that again. So we're not allowed to run line 11. We jump down, we run line 13, we run 14, we come back up. Everybody's allowed in the loop. We go in, and this goes around and around and around until we get to 70. 70 by 70 is 4,900. 4,900 is not greater than 5,000. We're not allowed to run line 11. We run line 13. We run line 14, which increases our loop or our square, increases the value of x to 71. Back up. Everybody's allowed in the loop. 71 multiplied by 71 is 5,041. Put that there. 5,041 is bigger than 5,000. So we are allowed to run line 11, which stops my loop and immediately spits me out below the loop. So below line 15. And so we won't go around again. Why would you want that compared to that? Can anyone think? Why would I change my evaluation up here and not have that, but have an exiting point somewhere in the middle of the loop?
Is it so you can put another loop inside?
I can put another loop inside this now, so it's not necessarily that. If anything, if you have a loop inside a loop, the break command gets more complicated because it only quits one of the loops. Okay. The reason why I might want to change from this to something like this, where I have to use the break command, and I don't always have to have true here, I can have an actual expression, is imagine I'm searching for a particular number, and I don't know what that number is until I get inside the loop. And maybe the range that I'm searching through is very large. If we think about integers, we have the possibility of 2.4 billion positive numbers. Now, if I find what I'm looking for in the very first number I check, I then waste 2.4 billion minus 1 searches. And we don't know how many processor cycles that might be. Let's say this is 1 processor cycle per loop. It's still 2.4 billion processor cycles. That's 1 that I've gone through. So the break statement might be a way of saying, I'm going to try to make my code a little bit more efficient by saying there is no point in searching through all of the other parts. I've found what I'm looking for now. I know my computer's fast and will get through the remaining search field pretty quickly, but I'm going to try to save those little processor cycles to try and make my code a little bit more efficient. So that would be one example of where we might use the break. If we keep running for the full 3 hours this evening, we will come across an example where I'll highlight where that can speed up your program slightly. The problem is, for first year and for the size of the programs we build, even using the break command, you probably won't notice any difference. Computers are so fast now, they do the calculations so quickly, it won't make a difference. But where it does make a difference is when you have a very large program and you're processing hundreds, if not thousands, if not hundreds of thousands of pieces of data. And if you can save a couple of hundred processor cycles across every one of those, that really builds up to seconds, if not minutes, of processing time. There's that example. Okay. And there's another example there. So I've removed the break statement here and the if statement. but I've kept kind of the computation out of the while loop there. So I've done squares equal to x by x for the very first time. Is square less than 5,000? If it is, these two are the same. And then I recalculate square and I go back up, and then square has a new value which I'm going to check. 3 different ways to solve the exact same problem. All of them as valid as each other. All of them effectively the same cost to the computer from a processing point of view. But it illustrates that there are different ways of doing problems, different ways of solving. They all have the same outcome. If you ran these programs and you didn't get to see the code and just ran the programs, you wouldn't know the difference between the 3 of them. As programmers, you should be aware there's different ways of solving problems. And there's not one way, and you can only ever do it this way. If any lecturer, here, outside, online, tells you this is the only way you can ever do this thing, I would be worried about that environment, that class. Because every single program has the possibility of being written in different ways. Maybe the changes are very small. Maybe it's just where you call the methods or what each method does. Methods something we haven't covered yet. Or maybe there are very large changes. Okay, this is only a 15-line program, and we have 3 quite different ways of doing it. And if you extrapolate that out to a 500 line, a 5,000 line, a 5 million line program, they could be drastic changes from one version to another version. But there are always multiple ways of solving every problem. Okay. Right, so what I have got left is basically illustrative programs, which is things I was going to do live code as part rather than doing slides. We've basically gone through all of the slide content for today. It is 10 to 8. If you want to take a break now, we'll come back. We'll decide who wants to put themselves forward as a class rep. And then we'll decide, do you want to put a pin in the class now? Or we'll do the live code stuff next week with revision kind of built into it. And then that means you can have time both weeks to work on assignments. Or do you want to keep going this week and then just do revision next week? So we'll say 15 minutes or so. So you come back roughly 8:05, we'll work from there.